So welcome. So last time we did about momentum, mass times velocity, and we did about impulse, which is force times the duration the force is applied for. And then what we found is that impulse equaled the change in momentum, which is not obvious, but it's true. And then looking at those, we found that the reason why we like momentum is because it is conserved from the beginning to the end of a collision. And we learned about the three types of collision. There's basically elastic, where energy is conserved and momentum is conserved. And then there's inelastic, where kinetic energy is not conserved, but momentum is still conserved. And there's a special case of inelastic called perfectly inelastic, where not only is there the collision where kinetic energy is not conserved, but momentum is conserved, but the two objects stick together. Can you see how an explosion is the opposite of a perfectly inelastic collision? Two football players tackling each other is like a mass splitting apart. So it's just the same mathematics. It's just you're reversing the order of things. And they're really useful. Okay, so now we're going to talk about work and energy. And that leads us on to power. And that leads us on to efficiency. So we've got a few things to talk about. We're going to start with work, because work enables us to store energy. So let's talk about language for a minute. Does it make more sense for me to say, that car has work? Does that make sense? You wouldn't say that, would you? Would you say that car contains work? No, you wouldn't say that. Could you say that car does work? You could say that car does work. Could you say that car has energy? Yeah, you could say that. Could you say that car contains energy? Yeah, you could say that. Could you say that car does energy? No. We don't do energy. We do work. We don't contain energy. We contain work. We don't contain work. We contain energy. So in our language, we recognize there's a difference between those two things. And yet they are measured in the same unit. They're measured in joules. And I think of it as a bit like you get paid a salary in dollars, which then goes into your bank account and becomes your spending money. And the act of getting paid is your salary. It's an act of transferring money from somewhere to somewhere. That's like work. Work is really transferring energy from somewhere to somewhere. You've got to have energy to do work, and when you've done the work, you've given that new thing the energy. Okay? So that's kind of where we're going. So then the other little wrinkle is, so work is really done by forces. It's not done by an object. So we talk about me doing work, but that's really just, that's the biologist speaking, yeah? It's really my lifting force does work, or my pushing force does work. So to begin with, at least, we should be trying to be careful about saying which force does the work. Later on, we can, get more casual, but to begin with, we need to link work with forces. And work is mathematically equal to the force times the distance the force moves through in line with the force. Yeah.
Isn't that kind of similar like having a voltage source and having the voltage source be the pushing force, I guess you could say, through a circuit, and the current be that energy dissipated throughout the entire circuit?
So that's a very interesting point, actually. So I think of current as being, to be honest, a whole bunch of buckets carrying energy, and that energy is dissipated through. But yeah, there's some quite good analogies between the mechanical world and the electrical world, yes. So let's start off. We're going to say that work is the force multiplied by the D means displacement. And I'm using for those of you who go on, you're going to see these symbols. And for most of us, we don't need to worry about the dot. It just means multiplied by. But for those of us who go on with physics or engineering, that dot is a reminder that the force... Oh, I'm sorry. I always forget to do this, don't I? Let's go back. Oh, wrong way. So I'm going to find my pen, which is down here. I discovered that down here we have some little symbols in very small colours. And let's do, what a green. I'm feeling like green today. So the force must be in line with each other. Now, that's not obvious. But it's not any old force times any old displacement. So if I have a force that's going to the right, and I have a displacement that's going to the right, then happiness, you just multiply them together. If I have a force that's going up, and a displacement that's going to the right, then happiness, they equal 0. Either way, it's kind of easy. If I have a force going up and a displacement going like that, we don't care about it. I'll give you, because that involves trigonometry. We don't get to trigonometry. So what I'd have to do in this case is I would have to tell you, oh, it goes that distance vertically, and it goes that distance horizontally. I'd have to give you those two numbers. And then you'd say, oh, well, if that's vertical, I go with that one. Does that make sense? So I say work is force times distance, but they've got to be in line with each other. And whenever work is done, well, a force is applied and an object is moved by the force. It's the force that actually keeps moving. If I just jerk something forward and the object moves forward, but my pushing force ends, I'm not getting extra work because that object's moving forward. That's just momentum. I got to keep on pushing and moving. So work is measured in joules, J, named after Joule, who was a famous scientist. So how much work is done by your lifting force on a 0.5, on a 5 Newton bowling ball when you carry it horizontally across 4 meters across a room? So here's the bowling ball, and here's you carrying it. And man, that's a bit unhappy. And it's a 5 Newton bowling ball, so the weight is 5 newtons. Now, if you're carrying it, it's in equilibrium. We learned about that. So the upwards force is 5 newtons. Yep. And you're carrying it by 4 meters. So there's my force. There's my lifting force. And ask about my lifting force. So there's my lifting force, and here's my displacement. So can you vote on this, please? What's it going to be? Is it going to be 20 joules? Because you took the 5 and you multiplied it by the 4? Or is it 0 joules? Because you didn't. Think back about your definition of work. You know, which one is it and why? And we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. Got about 15 people. So we're almost there. A couple more people. You want to have a go? I'll give it another 5 seconds. End at 40. Okay. So what we got? So mainly B, still some A. So here's the problem. Yeah, work is, so yeah, I understand what's going on. Work equals force times distance. So it's tempting to take that 5 and multiply it by that 4, but they're not in line with each other. In fact, you make no displacement vertically. You're going nice and horizontal. So if you like, the vertical displacement is 0. So it would be actually 5 by 0, which equals 0 joules. So it's actually B on that one, yeah? So it's got to be in line with the force. How much work is done by your lifting force on a 5 Newton bowling ball when you raise it 1 meter vertically? So here's the, man, my guy, and here's the bowling ball. And it's a 5 Newton bowling ball, so it weighs 5 newtons. So that means his lifting force must be 5 newtons. And really, I would say when you raise it steadily, because I don't want to imply, in fact, I just did the homework and I was careful about this. I don't want to imply it accelerates. It moves nice and steadily upwards, so there's no acceleration. So that would be 5 newtons upwards. And it goes up, so let's draw after picture. Don't know if I can draw the guy again, but, and now he's bent his arms and it's here. And that distance is 1 meter. So what do you think now? Flying in there. Yeah. Notice how his heads get smaller as he lifts more and more. Almost there. Let it go for until 30. So, and remember, I can't tell if you're going to do it. So who's doing what? So if you know you're not going to do it, just put in a number, and then we know. But if you're thinking about it, keep thinking about it. Okay, I'm going to stop there. So, and most people are saying A, and that's the right answer. It's, we say work is equal to force times my displacement, which equals 5. In this case, times 1, which equals 5 joules. Interestingly, where did those joules go? They went into the bowling ball. How do you know? Because if I put something into the bowling ball and I just let it go, the energy comes back out again as sound. So I store energy in, and then if I let it go, it comes out again as sound. So that energy is just moving from one place to another. So when you get work done by a force on an object, often the amount of energy in the object increases. But here's a funny situation. We have a baseball player, and he's sliding towards first base. Now, his displacement is to the right, but the friction force, which is the force that's been moved through a distance, is to the left. And if you take into account the different opposite directions, we'd say that that work is negative. Oh man, how can you have negative work? All that sign means is that you're taking energy out of the object rather than putting energy into the object. In this case, we're taking energy out of the object. And so the baseball player has less energy after he slid into first base than he had when he was running at full speed. So that negative or positive sign is a way of bookkeeping. Now, I'm not gonna try and catch you on that. I just want you to see it, that, oh, positive work means I'm increasing the amount of energy in my object, and negative work means I'm decreasing the amount of energy in my object. So we're getting, it's like heating is like positive work, and cooling is like negative work. It's a bit like that. Okay. So that was quick. There is one more. Is there one more I want to do with you? Yeah, there's one more I want to do with you. And supposing we had, let me come down here for a second. Yeah, I'm going to go there. I'm going to get my eraser. Oh no, no, I don't care. I want to pose another question, just because this is as difficult as it's going to get, and I want you to see it. Pen. So here's my crate and my lifting force. Well, if this is a 2 Newton crate, this is a 2 Newton lifting force. and I'm going to steadily climb a ramp. And the ramp is 6 meters tall. Actually, I'm going to call it 3 meters tall, because I know these numbers. And the ramp is 4 meters across. And I know, because I know a bit about triangles, that if one side's 3 and the other side's 4 and it's a right triangle, then that side is 5 meters up the ramp. So the crate starts off at the bottom of the ramp and it ends at the top of the ramp. So the crate has been transported through 5 meters. There's no question about that. But the question is, how much work was done by my lifting force? So you've got to look for your lifting force. And then you've got to decide which of these displacements you're going to work with. Is it 2 times the 4? Because you went horizontal. Is it 2 times the 3 because you went vertical? Or is it 2 times the 5 because you went up the ramp? It is actually 2 times the 3 because it doesn't matter about going up the ramp. What matters is the displacement in line with the force. And that's about as tricky as they get. So just get that down. Cool. So I try to be careful about copyright. So I'm trying not to use pictures out of the internet. I go to, what is it? It's not Wiki Pictures, is it? It's called Wiki Commons or something. So they got copyright. They're no copyright. The other thing I do is I take a picture of my stuff. So this is actually my car engine, which is like, yay. It's like little Honda. It's a little Honda engine. Very clean. I don't know why. It's about 2 years old. And it's when I got my first car, it was covered in oil. And, you know, it didn't run very well. And that might have been why, you know. This thing, I've never done a thing to it, and it just keeps running. So let's talk about power. My brother's an electrical engineer, and he kind of razzes me about being a physics person. And he says, you guys, you don't know what you're doing. I go, what do you mean we don't know what we're doing? You know, we make all this important stuff. And he said, no, you have the ideas for it, and then we engineers, we do it, we make it. You guys just like have a back of an envelope. And he said, but there are differences. And I've noticed his language about things is different to mine. He's an expert on motors. And he talks about motors in a very different way than I talk about motors. But that's a bit like if you go talking to a keen angler, keen fisher person, they talk about the stuff. And they use some of the same words, but a lot of the stuff they talk about, I have no idea what they're talking about. The tides and all that, I have no idea. So it's specialized language sometimes. But he said to me, the difference between a physicist and an engineer is that a physicist cares about energy, whereas an engineer cares about power. And I'd actually noticed, it's exactly right, because I had noticed that as I became stronger as a physicist, I began to realize that you can solve a whole bunch of problems by looking at the energy. All those kinematic, all those velocity and acceleration and time problems, you can actually do them all by energy when it comes down to it. In fact, there's a movement in physics to forget all about the kinematics. Who cares about it? It's just bookkeeping. Just teach them about energy and they can do all that. And there's a fair amount of truth in that. So I found that energy became my friend. I could figure stuff out by dealing about energy. I said, well, what's wrong with that? What's wrong with caring about energy? And my brother says, okay, so you get this message from, you know, the Pharaoh. And he says, can you build me a pyramid? He goes, you guys will go, yes. And 5 generations later, the pyramid is built. What the Pharaoh means is, can you build me a pyramid? Can I have it ready in 5 years? No, that's not about energy, that's about power. How quickly can you get the job done? So power is actually really important. And we tend to tack it on at the end, and we tend to forget about it. But power is actually really important. So we have, and remember, you get these equations on your exam. You don't have to remember these equations, but you know, after a while, you kind of like, you know them anyway. I'm having trouble finding my pen. There we go. So what we do is we say power is equal to work if you like, the amount of work done over the amount of time. We say power is the amount of work done over the time it takes to do the work. An engine of great power can do work rapidly. Power is measured in watts, named after James Watt. And horsepower, actually. Traditionally horsepower, nowadays watts. Oh, actually, still horsepower. If you go down to Home Depot or Lowe's and you buy a lawnmower, they'll sell you a 10 horsepower lawnmower. And I remember buying one and mowing my lawn and thinking, man, this is like having 10 horses pulling this machine. It doesn't feel like 10 horses, but it feels, you know, it's like, man, this is weird. But if you buy a lawnmower, say, that was made in Europe or some other place, it might well be measured in terms of watts. We tend to measure power to do with electricity in watts. Mechanical, we tend to use horsepower. Other countries use only watts. So a watt is a joule a second, whereas a horsepower is 746 joules per second. So there's a big difference between watts and... can I visualize a watt? A watt is a joule per second, and a joule is 1 Newton moved through 1 meter per second. And my visualization of that is 1 Newton is an apple. And 1 meter is going and putting the apple on my desk. So 1 watt is putting 1 apple on our desk every second. Does that seem like a lot of power? Not that much, does it? And a horsepower is putting 746 apples on my desk every second. So horsepower is considerably more power than a watt. Do you want to know a funny story about the horsepower, though? Because it was actually Watt that decided how big to make the horsepower. I think it was either Watt or Stephenson. So it might have been Stephenson. So there were 2 engineers, Matthew Boulton, and I think it was James Watt. I gotta research this. Matthew Boulton and James Watt, I'm going to say. And they were making steam engines at the beginning of the Industrial Revolution. And they were made for coal mines. So you dig the coal out of the ground, you put the coal into this machine, it burns the coal, it pumps the water out of the mine so you can dig deeper. So it's like, I mean, it's the most amazing thing. It's like feeding corn into a combined harvester. You know, the more you make, the more you can do. It's kind of like, it's ideal. And then they had this clear idea of, why don't we just make a building and put one of these engines in there? We can have the coal delivered, and we can have, rather than a water wheel or a windmill, we can have a factory. And that was the beginning of factory revolution. You could have a factory where you wanted it. You didn't have to worry about the wind. You didn't have to worry about the water. You didn't have to worry about having animals go around in circles. Oxen. You didn't need oxen anymore. You just needed coal. And so they wanted to sell these things. Well, people, you know, well, how good is your engine? They didn't really have a word for it. I mean, how great is it? How powerful is it? There was no measure for it. But factory owners, being relatively rich people, knew a lot about horses. So they decided, well, let's make it a horse equivalent, you know. So you got 3 choices, because horses don't come in the same sizes. So there's little horses, and there's average horses, and there's big, strong horses. And, you know, half the people have a horse that's stronger than average, and the other half of the people have a horse that's weaker than average. So it's a kind of weird kind of scale, because, you know, if you're used to stronger horses than I'm used to, then we're going to have different expectations. So it's kind of weird, really. Now, if you're in sales, you try and make it so that the customers go away happy. So they had three choices. They could try to get the horsepower unit as being the power of the average horse, or they could make it deliberately overestimating what a horse can do, or they could make it deliberately underestimating what a horse can do. I'm going to give you three choices. Do you want to overestimate what a horse can do? That's A. Do you want to match? You want to get the average of what a horse can do, or do you want to deliberately underestimate? That's C. So if you think the best thing to do is to overestimate what a horse can do, press A. If you think that the best thing to do is to try and do your level best to get the average of what a horse can do, I'm sorry, my eyes are a bit cloudy today, so I'm having trouble seeing them. And if you want to say that you should underestimate what a horse can do, press C. So, just a little bit longer. Yeah. Okay, let's call it a day. And let's see. Ooh. So here's the problem with the average. Most people said the average. Here's the problem with the average. Half your customers are going to be ticked off. Because you're going to say, quite honestly, this is a 5 horsepower engine. And they're going to say, oh, I'll replace 5 of my horses with it. And they're going to find that your engine will not replace 5 of their horses because they have big horses. They're going to say, only replace 4 horses. You cheated me. Now, you said, but you've not got the average horse. I don't care. You didn't say average horsepower. You said horsepower. So they're going to be disappointed. So not so good for that. That's from a sales point of view. From a science point of view, good. But not so good from a sales point of view. If you deliberately underestimate what a horse can do, so you say, oh yeah, this'll replace this, so a horse can only do this bit when in fact a horse can do more. So you say this is a 6 horsepower engine, but really horses can do more than that. Then you're going to disappoint everybody. Because they're all going, hey, come on, I took 10 horses, you know. So that's no good. What they did was they deliberately overestimated what a horse can do. And what happened was at least half the people, if not 3/4 of the people, if not all of them, said, I just bought a 5 horsepower engine from Bolton and Watt, and I replaced 5 horses, and it was hardly breaking a sweat. So I've replaced 10 horses. I'm 5 horses ahead. You better buy one before they catch on, because it's a deal. And they didn't care. They were just making up a number. They didn't care. Yeah, comment.
You said underestimate? I thought you meant...
I know. I always get confused about that, but that's yeah. If you kind of got the idea about you want to make the customer happy, that's the important idea, you know. And it matters. I mean, we don't tend to talk about how much we get paid. We don't tend to talk about how much we pay for cars. Think about it. Car costs you what, $20,000? If you get a $200 better deal than me, I'm upset. Why didn't I get that $200? It's like, what, 1%? Maybe, yeah, it's next to nothing. Is it 1%? Yeah, 1%. And yet I'm upset about it because it matters. It's like we want that feeling of happiness. We want that feeling that we got a deal. So salespeople will specifically try and work on making it so that you feel you got something. So they'll have these promotions and oh, you got the weekend special. You know, what does a weekend special mean? You know, is there some divine law that says on weekends you get specials? That, you know, it's important. So there's a case where science was affected by sales. It's kind of a very interesting situation. So let's try some of these. It takes 2 seconds to lift a 6 Newton block 4 meters upwards in the air. What power did you expend? So let's have a look. We have a 2 Newton block means its weight is 2 newtons. And that means your lifting force is 2 newtons. And you lifted this thing 4 meters. And the clock, there's my clock, says 2 seconds. So I'm going to say power is equal to the work done over the time taken, which
weighs 6 newtons, right?
So the block weighs, thanks ever so much. You saved my bacon there. That was like 6 newtons, 6 newtons, yeah. So the block weighs 6 newtons and 4 meters upwards, and then the time was 2 seconds. Thank you. So the amount of work done, well, that's the force times the distance in line with the force over the time taken. So this is going to be 6 newtons, and the distance in line with the 6 newtons is 4 meters over the time taken is 2 seconds, which equals 24 over 2. So the power is equal to 12 watts. See how you do it? Let's practice it. Let's do the next one. Can you guys do the next one for me? What I'm going to do is I'm going to put it on pause. So let's have a look at that. So let's stop that, and then let's have a quick look. And most people are saying number 1. So let's have a look. So I'm going to say, well, my power is equal to my amount of work done over my time taken, which equals the force multiplied by the displacement in line with the force over the time taken, which equals, now look at my diagram, and I say, well, that's a 2, and that's a 6, and that's a 4. So my power is going to equal, well, I can do that. It's going to be 12 over 4. So my power is going to be equal 3 watts. Yep, that one. Can I skip that next one just in case, because I'm running out of time a bit? So I'll leave that one for practice. Yeah, okay. So this is the next thing, and some people find this really easy, and some people find it kind of frustrating. But it's if you do twice as much work in the same time, by what factor did your power change? So I'm going to put the thing on so you can answer that and see what your intuition says. Sometimes people say, well, hold on, power is equal to the amount of work done over the time taken. And then they say, okay, twice as much work, same time. And they can get it like that. And other people have to put numbers in. Okay, so I'll give it just a couple more. I'll give it to 45 seconds. Okay, stop it there. And what we're saying. So most people saying C on that. And let's have a look. So what I do is I say, well, there's a formal way of doing this. I'll do it slightly informal. And if I double that and I same on that, then this side must be double. So the answer should be C, yeah? Agreed? There's a formal way, and if your gut doesn't tell you, this is what you can do. I'll show you it. So the new power over the old power is equal to the new work done over the new time over the old work done over the old time. And then you say, well, I don't know what the new power, I don't know what the new work is, and I don't know what the old work is, but I know it's twice as much, so call that 2 and call that 1. And it seems to me that the time is the same, so I don't know what it is and what it was, but I'm going to call it 1 and 1. So I get, oh, hold on, that equals 2. Then you say, oh, look, it's twice what it used to be. So I can do it formally, or I can do it informally. Now, if you were going on to do engineering or physics, we'd teach you the formal way to do it, because we not only change the power, we change the work, we change the time, we change 5 things, and you've got to figure out, you know, one's double, one's triple, one's halved, one's quartered, and you've got to keep track of it. But for what we do, often you can just intuitively get it. Let's try one more. Sorry, yes?
Something interesting is you can actually use some of this to figure out your electric bill. All we would have to do is we would take the voltage and the current, multiply those together, get the watts, multiply the watts by the amount of hours on average, or however many hours you use the appliance, and then convert that into kilowatt hours and multiply that by whatever the electric company charges you per kilowatt.
That's exactly how to do it. That's exactly how to do it. You get charged for energy using kilowatt hours. And kilowatt hours is power times time, which is energy. So the power company sells you energy. It's kind of a funny circumstance. That's exactly right. So let's do one more. If you have the same amount of work in half the time, by what factor did your power change? And let's, again, I'm sorry, my eyes are just a little bit cloudy today, and so I'm having trouble seeing that little dot. So what do you think on this one? And again, the more times you write it down, the more ingrained it becomes. And this is half, and that's the same. So what do you think? I'm going to give it until, I'll give it a few more. I'll give it until 40 again. We've got time. Did I mess up? So if you do the same, oh, I am, again, thank you, man, you guys are just saving me today. Did the same amount of work in half the time. That's like 1 over a half, which is like 2, isn't it? I was going to get that one wrong. I was going to say halved, when in fact the answer is doubled. What did the class say? Did I mislead you guys? So I caught half of you and the other half, yeah, but just ignored me. Sometimes a good thing to do. So yeah, sorry about that. Okay. So there's an interesting point. How many people prefer the numbers? How many people prefer the ratios? It's kind of interesting, isn't it? Everybody kind of assumes that fundamental physics is easy because there's not much math in it. And I think it's hard because there's not much math in it, you know. It's like numbers really, for me, simple numbers kind of solidify things. You won't get things backwards. But this is all about your engineering gut or your science gut. It's like, do you have a feel for which way it goes? And that's whether you, no matter what you're going to do. Whenever there's a system that changes, which could be sales, it could be marketing, it could be cooking, it could be building, it could be engineering. Whenever you get systems where you affect them and there's an outcome, over time you build up your intuition about what you expect. And because your brain is good at figuring this stuff out, even if you don't have an equation, you get better and better at it. You know, that's why experience gets paid. Okay, bit of a line. We've done work. We've done work per second. Where does this energy go? Well, I've just said it. Where does the work stuff go? The energy gets stored inside an object. As far as we're concerned, there are 2 types of mechanical energy. There's so-called potential energy and the so-called kinetic energy. Actually, I think the book has a third type, and that is spring potential energy. Or maybe not, but certainly my notes used to have spring potential in it. And that's the compression or expansion of a spring. And I decided to take it out because it's like, it just makes it a bit long. So we're going to talk about potential energy, meaning gravitational. And that is defined as the energy because of the position in a gravity field. Sounds a bit technical, a gravity field. The Earth has a gravity field around it. If I move the position of a mass inside that gravity field, then it has a different amount of potential energy. I can say my change in potential energy equals mgh. The mass of the object times g. This is so we tend to get told that g is, well, anybody want to tell me what g is? Well, yeah, that's a word. Can you be a bit more? Yeah, now you're giving me the number. 9.8 what? Ah, that's right. Now, that's wrong. Because that's what we get told. We get told that g is the acceleration due to gravity. And the reason why they tell you that is because it is the same number, and you have done about acceleration. So it's like, they know about acceleration, so let's just... And it mathematically is correct. But really, g is your gravitational field strength. And the reason why we kind of shy away from that is because, gravitational fields are kind of abstract things. The units are actually what give it away. It is the number of newtons you get for every kilogram. It turns out it's 9.8. But it really is your gravitational field. I prefer 10, by the way, because it just makes my life a lot easier. So m is the mass, and g is the gravitational field strength in newtons per kilogram, and h is the change in height. Yeah. And then there's another energy which is called kinetic energy, and it's a half times m times the speed or the velocity squared. Yeah. This is a bit weird. Here, if I double my change in height, if I climb a hill that's twice as high, I store twice as much potential energy in me. I have to do twice as much work. But if I go twice as fast, I store 4 times the amount of kinetic energy in me, which means I have to do 4 times the amount of work. That's why your gas mileage is lower if you're going faster. If you go at 70, you get about half the gas mileage that you get at 55, because 70 squared versus 55 squared. Yeah.
Does the gravitational force change when you go higher into the atmosphere?
So, the gravitational force, very good question. The gravitational force falls off as you go higher. I wouldn't say into the atmosphere, because the atmosphere is only about 20 miles. Into space. And it's not because there's no air. So people have this idea that you have gravity inside the atmosphere, and then when you go into space, there's no gravity. And that's not true, actually. If I go, we're 3,000 miles from the middle of the Earth. Yeah? The Earth is like 6,000 miles diameter. So we're 3,000 miles from the middle. If I go another 3,000 miles out into space, my g, gravitational field strength, is basically a quarter of what it is here. Yes, it's a quarter of what it is here. So 20 miles is not going to make any difference. 20 miles. So you're right, in principle, the pull of gravity gets less as we go further and further out, but we've got to go a long way before it's really noticeable. Okay? We're going to pretend we're in a room so that we don't have to worry about it. you know, because otherwise it gets complicated. That's a problem we look at in engineering physics and also probably in algebra-based physics. That's a problem we look at. But it's we need calculus to solve that one. Okay. So, kind of weird. This one here, if I have PE versus H, it goes as a straight line. And this one here, I have KE versus velocity. It goes as one of these curvy things called a parabola. Okay. Put these two guys together, and that's my mechanical energy. So my mechanical energy is the sum of my kinetic and my potential energy. Yes?
Is the kinetic energy the integration of the momentum?
Is the kinetic energy what, sorry?
The integration of momentum.
So momentum, oh, that's an interesting question as well. So momentum is mass times velocity. And if I integrate it with respect to what?
To velocity.
To velocity. If I integrate that, that would be mv squared over 2, a half mv squared. Whoa. I am very impressed. I've never thought of it like that before. Okay, but mathematically it works out. Yeah, I've never thought of it like that. I've got to think about that. But mathematically it works out, yeah, cool. You don't need to know that. Okay. Because I just found it out. Very interesting. So let's do some of these. If you lift a 4 Newton block 5 meters up into the air. Oh, so one final thing. If you do work on an object, it's going to store energy in that object. Agreed? One of these two has to change, or both. Bit of both, or one or the other. The work you do is going to equal the change in mechanical energy. You could use that to raise something in a gravity field and not have speed. I could use it to give it speed and not raise it in a gravity field. I could do a bit of both. So it's going to change. Something has to change. Unless I convert it to heat, and then everything gets hot. We assume there's no friction, so we're assuming that won't happen. So something has to change. It's got to manifest itself, we say. The work manifests itself as being a change in kinetic energy, or a change in potential energy, or a bit of both. Okay. Now we do a whole bunch of sums where we look at that. So we say, okay, if you lift a 4 Newton block, that's 4 newtons, which means my lifting force is 4 newtons, 5 meters in the air. What's this change in potential energy? So I'm going to go PE equals mgh, which equals the, oh man. So here's a little bit, I'm a little bit of a tricky here, I'm being tricky. Did I tell you, I don't know if I did, that W equals mg? Did I tell you that? Probably not. So weight is equal to the mass times this gravitational field strength. So that there is weight, which equals W times H, which equals 4 times 5, which equals 20 joules. That was a bit more complicated than I expected it to be to begin with. So there's a little wrinkle there where I didn't give you the mass, I gave you the weight. And the weight already has G included in it. So when you see a weight, think of mg, okay? When you see this mgh, think of, oh, it's the weight times h. It's a bit of a wrinkle. It's not where we usually begin. We usually begin down here, where we have a 4 kilogram mass. Oh man, I'm running out of time. 4 kilogram mass, and that goes 5 meters. So what would happen here is we say, well, PE is equal to mgh, which equals 4 times 10 times 5, which equals 200 joules. which is that one. So can you see, again, it's this mg. This time I gave you the mass, and you have to know the g. G's always 10. Whereas here, I gave you the mg. And more often than not, it's going to be this middle one. I'm going to give you the mass. More often than not. This one down here, this is 2 newtons down, which means my lifting force is 2 newtons. I have my 8 meters. So I'd say PE is equal to mgh, which equals W times H, which equals 2 times 8, which equals 16 joules. Cool. I'm going to have a quick look at my thing to see when am I running out of time. I've got 10 minutes. Okay. It's all right. There's,
kilograms instead of newtons, that's what you multiply the 10 in?
yes. Yes, that's exactly right. Don't worry about those. Is that right? There's more of the same potential energy. Okay, I want to move on. When you are driving at 90 kilometers per hour, how much more distance do you need to stop than if you're driving at 30 kilograms per hour? Can you get it? I would not ask you this on a test, but can you get it? Can you guess? Remembering that kinetic energy equals 1/2 mv squared. And this guy is 3 times bigger than that guy is. So what do you think? I'm going to let go for just a few more seconds because I want to move on. Okay, let's have a look. Oh, yeah. Okay. So here's what's going on. The kinetic energy goes as v squared. So if this is 3 times bigger, it's got 9 times the energy. Yeah? If it's got 9 times the energy, you got to do 9 times the amount of work to get rid of that energy. And the way you do that work is you squeeze on a brake pad and then you roll. If I squeeze on a brake pad to the same extent and I've got to get rid of 9 times as much energy, I've got to roll 9 times as far. So the answer actually is that one, but it's not obvious, it's not trivial, and you know. So that's an advanced question. True or false, an object can have energy? What do you think? Yes. True or false, an object can have work? False, yes. Work energy theorem. You do work, you change energy. That's basically it. You do work, you change energy. You do work, you change your mechanical energy, and that's made up of kinetic and potential. So let's play with this. If you perform 40 joules of work pushing a 2-kilogram cart along a level track, how much kinetic energy have you added to your cart? Kinetic because I'm not going up a hill, so there's no change in potential energy. So I say my bit of work is equal to my change in my mechanical energy, which equals my change in my kinetic energy plus my change in my potential energy. But I know that's equal to 0 because I'm on a level track. Agreed? So if I do 40 joules of work, then that must equal 40 joules of kinetic energy. Because none of it's going into potential because it's on a level track. So that's going to be 40. That makes sense? If you perform 60 joules of work lifting a 2-kilogram object into the air, W is equal to 60 joules. My work is equal to my change in my mechanical energy, which equals my little bit of kinetic energy plus my little bit of potential energy. But I know there's no change in kinetic because I'm doing it slowly. Incredibly slowly. And I say, well, that's 60, so that must equal 60. Ah, my delta PE must equal 60 joules. Sorry. If you do work that adds 30 joules of kinetic energy and 20 joules of potential energy, how much work did you do? The amount of work you did is equal to your change in your potential energy plus your change in your kinetic energy, and you added 30 joules of kinetic and you added 20 joules of that. So how much work did you do? 50 joules. You can tell my numbering gets weird down here. If you are on a roller coaster ride at point X, let's do a roller coaster ride. At point X, you have 20 joules of kinetic and 10 joules potential. So, whoosh, there's point X. Kinetic energy equals 20 joules. PE is equal to 10 joules. What's my mechanical energy? What's it going to be? Delta ME is equal to delta KE plus delta PE. My little bit of mechanical is equal to my little bit kinetic plus my little bit of potential, which is 20 plus 10, which equals at a later point on the roller coaster, you have 5 joules of kinetic. So at a later point, I have 5 joules of kinetic. My mechanical energy cannot change. That's the way it works. Roller coaster ride, constant mechanical energy. It's drifting backwards and forwards between height and speed. So what is my potential energy? So 30 minus 5 is equal to PE. So my little bit of PE is equal to 25 joules. True or false? An automobile consumes more fuel when its air conditioner is turned on. What do you think? You're driving and you put the AC on. Yeah, you're going to use more fuel because you're doing more work. An automobile consumes more fuel when the lights are turned on. You drive in, and then you turn the lights on. Yeah. An automobile consumes more fuel when its radio is turned on. Yeah. You're doing more stuff. True or false? Rows of wind power generators are used in various windy locations. The wind power unit generate the power wind power generator. The power wind this reduces, whatever it is, reduces the speed of the wind that blows through it. What do you think? Do you think the air slows down having gone through? Yes. Doesn't it? Because it's taken energy away. So it's got, it reduces? Yes. I'm going to hold it there. So I was hoping to get through this entire chapter, and I'm going to hold it there. And I've got a few more minutes, so I'm going to stop. Ooh.